theory of Leray of weak solution for the Navier-Stokes equation. So the idea is to use mollification, energy estimates, and compactness arguments in order to provide weak solution when the usual iterative process doesn't work. So, okay. So the Navier-Stokes equation I am studying is just defined on the whole space. There's no problem of border. That's an incompressible homogeneous field. And I will focus on the initial data U0, which is Leydens-free, of course, locally square integrable, but not square integrable on the whole space. So we cannot use directly the Leray theory. So what can we say? And how far can we extend the theory? That's the problem. That's the idea. So why study such solution? As a matter of fact, there is a paper of Bradshaw and Tsai of last year who studied discretely similar solutions of the Navier-Stokes equation. And for such initial data, which is just you have something which is a kind of homogeneity, but just for a discrete set of scaling parameters. And if you were really truly homogeneous, if it were true for all positive lambda, then locally square integrability implies uniform local integrability. And then I developed a theory 20 years ago to deal with uniform local square integrable, uniform square local square integrable data. But for when the set of scaling parameters is discrete, then we lose the uniformity. But we still belong to a weighted Lebesgue space. It means that we can integrate with a weight, which is 1/1 plus x to the power gamma, as soon as gamma is bigger than 1. So the idea was to look if there was a general theory for such data without the. So now, if we consider a solution which has a good decay, it means that good enough decay, it means good enough integrability at infinity, then the pressure is automatically given by the Riesz transform of the sum of the Rj, Uy, Uj. So the pressure is not an unknown, it's just a function of the velocity. So I will never bother to speak much of the pressure. I could rewrite the equation without the pressure. I will not do it. I will keep the pressure all along the computation. But in this way, this term is defined even when U is just is uniform locally square integrable, without the nabla, the term is meaningless for general U, but with the derivative it's meaningful, but it's not equivalent to the first equation. But in the setting I will work, the both formulations are totally equivalent. So the first theorem I will prove is that if you take locally square integrable function U0 which has some decay at infinity, so that this is satisfied, then you can find the global solution U to the Navier-Stokes problem, which will be locally N infinity L2 of the weight and L2 H1 in the weight. So how do we construct such solution? The idea is to follow the formalism of Leray, and then we will find eventually a solution which will be what is called the local weak Leray solution. It means that the equation is not is to be taken in the sense of distribution, but we want local integrability and differentiability, so that we have on every compact subset of R3, we are locally L infinity L2 and L2 H1. So such a term is well defined, for instance. Then for control, which will be very important for regularity issues, we have the Schaeffer inequality. If we took the product scalar of the equation with U, then formally we would find that dt of U square would be 2 U scalar dtu, and we will find inequality. But as a matter of fact, the scalar product dtu times U is not allowed because we have not enough integrability in time. So what we can find is just something with a mu, which is a defect measure. So we have a loss of mass. And then the last point, which is very important, is continuity as t equals 0. That's important for many problem of regularity, but I will not have time to develop this point. So let's forget. So the beginning of the talk is to recall some classical results who are 80 years old or 50 years old. Which are all based on energy inequalities. So the idea is how do you describe the energy balance for the Navier-Stokes equation at what can you read in this energy balance. So for constructing a weak solution, you're beginning to modify the equation by a little damping of the nonlinearity. U epsilon will be assumed to be L2. Then if you compute with a bump function, if you convolute with a bump function, it will be in L infinity. So the coefficient of the advection will be very small. That's the idea. And once you do that, it's easy to prove that you have a solution of the equation of the transport equation, which at least on some existence time t epsilon. And then the idea is to prove that t epsilon is independent of u epsilon. At least it can be bounded by below by something which is independent of u epsilon, and that on 0 t naught, you can find uniform energy estimate on u epsilon and go to the limit. So we will do that for L2, for H1, for H3, and then for weighted L2, and then a weighted H1. And so the idea is very simple. We begin with the energy balance. So let's say if we work in L2, we just take alpha equal to 0. If we work in H1, we will took alpha equal to 0 or 1, and in L3 up to 3. So we look at the energy balance. Because of the damping of the modifying, we can write that the derivative of the square is 2 times the derivative times derivative scalar d alpha u epsilon, and then we rewrite the this quantity. This quantity, we replace dtu epsilon by its value, and we reorganize the quantity. And we have three families of terms. We have the good ones, which are the blue ones. They are very good, and because they have a sign, they are negative. And then you have the not so bad guys, which are the red ones, because you can extract a derivative. So that in the sense of the distribution, that's a derivative of something which has a less derivative than the whole family. And then you have the bad guy, which is the orange one. The orange one, you have no sign and you have no derivative. So if you want to control something, there will be trouble all the time. The idea it will be, how do you use what do you do with the bad guy? That's the main problem of the talk. So we begin with L2. For L2, there's no bad guy because they are we have the chance, we have the luck to be lucky enough that there is no orange terms. There's only blue terms and white terms. And then when we integrate, we find that we have the L2 norm of u epsilon plus the integral of the L2 norm of the gradient of u epsilon is equal to a constant, which means that we have a uniform control of u epsilon in LNC L2 norm and L2 H1 norm. So that's the basis of the theorem of Leray, and it's easy by Reddish to prove that we have indeed a global weak solution in LNC L2 and L2 H1. Now, if you look at H1, we have orange terms. It means that we have some bad guys. The bad guys are all involving one derivative of u. Okay, one derivative here, one derivative here, and one derivative here. So it's not very difficult to deal with them. So if we integrate, we will find the derivative to the power of 3, and the derivative to the power of 3, the integral in x will be the L3 norm to the power of 3, and then the L3 norm of the derivative of u can be controlled by the L2 norm and the L6 norm, but the L6 norm can be controlled by the symbol F embedding by the norm of u in H2. And then by a Young inequality, we will we'll make appear the L2 norm of u in H2 to the power 2 and the H1 norm to the power 6. We replace. This term will be absorbed by this term because here we have 1 nu, here we have 2 nu. And then we have a nonlinear ground-wall inequality. And this nonlinear ground-wall inequality give us a uniform control on 0t, where t is given by as the order of nu to the power 3, which is here, and u naught to the power 4, because here we have 6, which is equal to 2 plus 4. And as we are making a ground-wall inequality on u to the power 2, we have to control u to the power 4. The main point is that this time doesn't depend on epsilon. So we will have uniform controls on 0t, and we can use control compactness arguments and find that we have a solution on the local time. When u naught is in H1, we will have a solution in LNCT H1. That's local in time solution, but we know that we have global solution when the data is small. And again, this can be seen on the energy inequality just by writing the interpolation inequality slightly differently. We wrote we wrote this inequality, and then just here we isolate one U naught H1, and the norm of U naught H1 is controlled by the norm of U2 in L2 times the norm of U epsilon U in H2. So we find this inequality. This can be done, for instance, by Cauchy-Schwarz. And then we have something like that, which means that as long as this quantity remains small, we have a control of U epsilon in norm H1. So we have a uniform control. And as the norm of U epsilon remains less than the norm of U02, we want this to remain small. But this is small when this is small. So we have a virtuous circle, and we get a global control and global existence as soon as the product of the two norms is small with respect to the viscosity to the square. And this is a very well-known result. It goes back to Leray and Ladyzhenskaya and Kato. There are many ways of writing it. So there's nothing very new. The main interest is to see that we have information from the energy control. Now, if you look at the H3 norm, then we still have our blue term or red terms, and the orange terms, they are bigger. The Leibniz formula goes bigger and bigger and bigger. But the main point is that we use not big derivatives of U. Here, alpha is of order 3, so there's 3 derivatives 1, 1, 3, 3, and 2, 3, 2. So we have to control, as we want to control the third derivatives, we have to control the L1, the 2 derivatives and the 1 derivatives. And this is easily done. Because we find if you have 3 derivatives, we want to control the L2 norm of the 3 derivatives. So in front of them, we have just 1 derivative. We will control the L infinity norm of the derivative. And if we have 2 derivatives, we find this 2 times, and 3 derivatives. Here we need the L2 norm of the third derivative. So we need, as we find the 2 derivatives 2 times, to control the L4 norm to the square. But we use the usual interpolation inequalities to find that this term leads to this control. And the H2 norm of U is controlled by the L2 norm of U times the H3 norm of U with the good exponent. So we have, again, a nonlinear control Grandwall inequality. And we get, once again, a uniform control as for T, which is of order 1 over U2 to the power 1/6 and U epsilon H3 to the power 5/6. And what is most important is that this time doesn't depend on nu. So as it doesn't depend on nu, we can let nu go to 0 and find as well a solution to Euler equations. So from the energy balance, we can find a lot of information. That's the idea for the classical solutions. Before introducing the weights, I will say just a few words to uniform local estimates, the theory I developed 20 years ago. So we take a partition of unity, which is invariant by translation, and we define the U-log norm by taking the supremum of each bump function times f. If L2 U-log, it would be the L2 norm, H1 U-log will be the H1 norm, and so on. And now we write the energy balance. We have to introduce the bump function in the energy balance. And again, we have the red term, the blue term, but in front of the red term, we have the bump function. So when we will integrate, the integral will not be equal to 0, but by integration by parts, the integral will go to the bump function. There's some technicalities on the pressure, but I have no time to comment on that. It's not very important anyway. It's well understood by now. So the point is that when we look at when we integrate, we find this bump function, and we want to control the square root of the bump function times u. Here we have 2u, so and we have one function, so this function should be controlled by the function psi j. Here we have 3 functions, square and 1. We have 3 functions, so we should control by the bump function to the power 3 over 2. And as a matter of fact, of course, that is not exact for a given j, but when we move a little the indexes, it becomes true. So we have just to check that the derivative of a bump function is controlled by the sum of the power of the neighboring bump functions to the power 3 over 2, and then we will find exactly something which is very similar to the ground wall inequality that we had before. And then again, we have a uniform control on a t, which is like the norm of u naught to the power -4. It's exactly the same thing as in diamond for the Lebesgue measure, except that we have to be a little cautious because some terms that disappear don't disappear any longer. We can do exactly the same computation for H1 and for H3 U-log norms, and then we find again existent times, which depends on the norms of u naught. And again, for H3 and let's say nu less than 1, the existent time t doesn't depend on nu, and then we can let nu go to 0 and find solution to Euler equations. And last remark, in the case of the Morey componental space M23, which is has to be in L2 U-log, and then to have invariant norms estimates for rescaling like L3, so the 2 and 3. Then I could prove that we have a global weak solution by only with the previous estimates, because we just rescale, then we have a solution which is associated to lambda u naught lambda x with the same time t than u naught, because we have the same estimate for the L2 u-log norm. And rescaling from L2 u naught lambda x to u naught, we will have a solution. Let's say that when we look at this solution, at this initial data, we find solution v lambda, whose existence time is t. Then we have a solution u lambda, which is associated to u naught by u lambda equals to lambda v lambda of lambda square 1 over lambda t over lambda square x over lambda. And it means that the existence solution of u lambda is lambda 2 times t. And then this is a constant, and this go to plus infinity. So we have a solution which is defined on larger and larger interval of times, and again by checking that we have uniform controls, and by using Reddish type arguments, we can exhibit a solution which is global. So the main tools in all the previous slides and the slides are uniform control, non-linear ground wall inequality, and scaling. And that will be exactly what we are going to do when we are going to study the problem with weights. So we begin with the easy case, the L2 case, which has been described by Bradshaw, Quoc-Hung, and Tsai, and by Fernandez and myself last year in a quite similar ways. So the idea is that I will not present for a specific weight, but for a class of weight, because I will have to consider two classes of weights, basically. So I put them in a big set of weights. I just ask 4 assumptions on the weight. The first one is that the weight is positive and less than 1. It means that, in particular, that L2 will be included in L2 phi. And that is interesting because we are going to approximate the solution by solution in L2 and then trying to find uniform estimates in L2 phi. The second requirement is that the gradient of phi is less than the phi to the power 3 over 2. When we look at the red guys in the energy balance, we have a different derivative in front of something which can be quadratic or cubic. So if it is cubic, when we make the integration by part, we will find the cube of u times the derivative of phi. And if the derivative of phi is less than phi to the power 3 over 2, then we will find the cube of the square root of 5 times u, and then it will be good for the nonlinear ground wall inequality. So the idea is very natural. The third requirement, we ask that for some rho in 1, 2, phi to the power rho belongs to the Mukhanov class A rho, and that is essentially aimed at controlling the pressure, because the pressure is given by the Riesz transforms, and the Mukhanov class A rho is given by the fact that the Riesz transforms are a weight W belongs to A rho if the Riesz transforms are bounded on L rho of W dx. So that's just aiming to control the Riesz transform. And then the last requirement will be to provide global solution by rescaling. So we have 4 requirements. We initially with Pedro Fernandez, we asked other requirements, but there are consequences of those ones. We asked that phi x is not too small, but this is a consequence of this differential inequality, and that phi belongs to the Mukhanov class A2, but this is a consequence of phi rho is in A rho. It's we could find that in the book of Stein, for instance, in the further results on Mukhanov weights and harmonic analysis. And now the examples I should deal with. The first one is the weights I have evoked at the beginning of the talk. Is 1 over 1 plus x to the power gamma with gamma less than 2, which corresponds to analyzing, for instance, the discretely self-similar solutions. And the second class of solution will be when I will consider axisymmetric solutions. So I will ask the phi of x to be to depend only on R. So I look at the cylindrical coordinates. Z is the vertical, it's x3, and R and theta are the polar coordinates for the plane x1, x2, and I want that the weight depends only on R, and I take 1 over 1 plus R to the power gamma, where gamma is less than 2. gamma equal to 2 is not allowed because it doesn't satisfy H3 or it doesn't belong to A2. So that will be the class of weights I will consider. And I will explain later why consider axisymmetric weights. So the theorem is the following one. If phi satisfies the assumption H1 to H2, H3, and H4, and if U naught is in L2 phi, then you have a global solution in L2 phi, which for every finite interval, it belongs to L infinity L2 phi and L2 H1 phi. And the proof, of course, is very similar to the proof of the results before, except that we have to modify the Leray's modélisation because we have to modify the initial value. Because if we let the initial value go have some increase in some directions, because if you are not uniformly locally integrable, so it means that sometimes you can be big, and then you have here a cubic quadratic term. We can inflate the growth, and then we cannot prove that we have a solution. We can prove by energy estimate, but that's what I want to do now. I want to begin with a well-defined classical solution. So I take I truncate U naught in order to have something which is L2. So I multiply by a truncation function, but then I kill the divergence-free property. So I use the Leray projection operator to have something which is both L2 and divergence-free. And then I will try to prove that for this equation, I can have existence time T epsilon, which is larger than some positive T naught, and have uniform energy estimates, which are enough to use Reddish arguments and go to the limit and find a solution. So the arguments are quite the same ones. So it's not very difficult to understand. Just some technicalities. First, why it is so important that phi is in A2. Since phi is in A2, those transforms are bounded on L2 phi, and then it's an easy consequence. U naught epsilon converges strongly to U naught in L2 phi. So it is no big deal to have transform for the L2 phi estimates to have transform U naught in U naught epsilon. Now, since the gradient of phi is less than phi to the power 3 over 2, but as phi is less than 1, it's less than phi, we find that if f is in L2 phi and grad f is in L2 phi, then the square root of phi f is in H1, and so it is in L6, and you can use the whole family of Sobolev embeddings and interpolating inequalities for square root phi of f. And now, moreover, the Hardy-Littlewood maximal transform is bounded on L2 phi. And if I take a convolution with a bump function, I have a pointwise estimate that phi epsilon. Petit problème. Voilà. That phi epsilon of f is controlled by a constant which doesn't depend on epsilon, the Hardy-Littlewood maximal function of f. So it means that if I want to estimate norm in L2 phi, I can forget the convolution. Now, why it is important that phi to the power rho belongs to a rho, because I have to control the integral of p epsilon times u epsilon times phi to power 3 over 2. And I will just use the L rho norm. So I can write that phi that is controlled by the norm of f phi p epsilon in L rho times the norm of square root of phi times u epsilon and rho over rho minus 1, for instance. And as p epsilon is given by this transform on the coordinates of u epsilon and u epsilon times phi epsilon, it means that and if phi rho is belongs to a rho, this one will be controlled by this norm which will be controlled by this norm, and then it's just a problem of writing the good interpolation inequalities between H1, H6, and L2, and we find that this integral will be controlled in this way. Now, if rho is too small, the problem is that rho over rho minus 1, if rho is less than 6 over 5, rho over rho minus 1 is larger than 6, and we have no control of square root of phi u in LQ for q bigger than 6, because H1 is controlled, is embedded in L6, but not in L6 plus epsilon. So we cannot use this estimate. So instead of using the L rho norm, we use the W1 rho norm, the Sobolev norm. And again, the Sobolev norm, the resistance norm will be controlled on the Sobolev norm, will be bounded on the Sobolev space, because you have just to look at it's a convolution operator, and you have to control the norm in rho and the norm of the derivative in rho, so you are controlled. So this quantity is controlled by this quantity, and again you use some interpolation inequality, and you find again a control like that. But this is when we used after the Young inequalities. That is what is leading us to the nonlinear ground-wall inequalities. So essentially, we have finished the proof. So we take the energy balance, we integrate the derivative, the right derivative gone on the weight. The weight is less than 5 to the power 3 to the power square, and then we find that we have a nonlinear ground-wall inequality and a uniform time, and uniform estimates on the uniform time, and then we can go to the limit. So we have a local solution. Except that in the theorem, I wrote that we wanted to prove global solution, so the idea is then to rescale. So we take U naught, we rescale, and we define V naught lambda as lambda U naught lambda x. And we know that we can find V naught lambda on an interval time 0t lambda, which is given by the norm of V naught lambda to the power 4. And then we rescale. And we have a solution which is not defined, which will be associated to U naught, but which will be defined on L2 T lambda. So on this quantity. And we just have to check that this goes to plus infinity as lambda 10 goes to plus infinity, and this is exactly the reason why we wanted to control 1 over lambda 2 phi of x over lambda by phi over x. So it means that that at least it should be a constant, but the situation is a little worse because we have a control, so that is bounded, and then punctually it goes to 0 because that is less than 1 over lambda 2. So this quantity goes to 0 as lambda goes to infinity. So this quantity goes to plus infinity. And then we can use again Rieusset type estimates to prove that we have a global solution. So the idea is just always the same one. we need new ideas when we look at the H1 problem. Because when we look at the H1 problem, okay, we have the blue guys that are very nice, the red guys that are quite nice, and the orange guys. And then when we integrate, we have something which is cubic, and phi is just writing the phi to this square. So that's quadratic. So we should control something which is cubic, but something which is quadratic, and there is no hope. So we have no theory for H1 weighted spaces. But we say that maybe we didn't take the good quantity to evaluate, because this quantity should be replaced by the vorticity. Instead. Why? Because we can do it because the derivatives of u epsilon are given by Riesz transform of the vorticity. And we know that phi is in A2. So the SL2 norm is equivalent to the SL2 norm. And as a matter of fact, maybe it's easier to control the L2 norm of the vorticity than the L2 norm of the whole derivative of u. Maybe. So we look at the vorticity. But the vorticity, to have a nice equation on the vorticity, we must forget any bump function in the equation. It means that I don't want to make the conversion of u epsilon with phi epsilon. This is not good for the vorticity. But we need a convolution in order to deal with the L2 case. In the H1 case, we have enough regularity to have the direct solution without the damping. So we look at the equation without the damping, but we keep the truncation in order to have the H1 theory of Navier-Stokes equation. And then we can write, in that case, the equation of the vorticity. And the vorticity is, the equation of the vorticity is quite similar to the equation of the velocity. And it means that we find the transportation by the flow u, dt u epsilon nabla u epsilon dt omega epsilon plus u nabla omega epsilon. We have the diffusion with the viscosity nu Laplacian of u, nu Laplacian of omega. We have no longer the pressure, but we have this term, which is known as the stretching term, and which is known as to be the very, very bad guy in the Navier-Stokes equation. And we will see that it is the reputation is normal because we will have some problem. Donc, we look at the energy balance, and again, we have a good guy, blue, not so bad guy, red, and the bad guy, which is orange. And what can we do with the stretching term? In dimension 2, there is no problem, because in dimension 2, this term is equal to 0. So everything is good. We have only good guys, and then we have a H1 theory with weights. There's no problem. But we are just in dimension 3. In dimension 3, we have to have something which quite like that, but not exactly like that. And there is one case where we can do that. That's the case of axisymmetry with no swirl. So we take a flow which is axisymmetric. U depends only in the basis of cylindrical coordinates. U depends as coordinates, which depends only on r and z and not theta, and moreover has no component on theta, e theta. So this is U. And then omega, the vorticity, is given in the direction E theta. And we look at the radial weight, which depends only on R and not on Z. And now we rewrite the bad guy as a good guy, and another bad guy, which again is not is still quadratic and is still quadratic, and there is no derivative. But this guy has a component on AR and E theta, and the component E theta contains derivatives of omega. But U epsilon is orthogonal to E theta, so the component of E theta is not important. And then on ER, the component of omega nabla omega is omega to the square over R. So we find this new term, and this term has become has turned from orange to red. Why? Because when R is small, then we have that 1 over R over U over R is like omega in modulus. So we have something which is quadratic, which is cubic. But when R is small, phi is like 1. So the phi we can find an extra exponent of phi, and so the cubic term will be integrated against the cubic term. So everything is good. And when R is bigger than 1, we have that 1 over R is less than the square root of phi. So again, we have a cubic term, and we will find a cubic weight. So everything is in good order and is well balanced, and we can make the computations. So we have the theorem that if we have an axisymmetric flow with no swirl, and if phi is the axisymmetric weight that can satisfy the properties H1 to H4, then we have a local solution of the Navier-Stokes problem, which will be local in time in L infinity H1 of phi and L2 H2 of phi. But here I have written that I have a global solution. Why global? And it's the end of the talk. It will be very easy to see that we have a global solution because we will use Ladyzhenskaya inequality. Ladyzhenskaya has proven in 1968 inequality for H1 flows which are axisymmetric with no swirl, and we will exactly use that inequality. So we have we write the energy balance, and then we are interested in that term, and we will control by the L2 norm of 1 over R omega, and the L infinity norm of square root phi u, and the L2 norm of square root phi omega. And by interpolation property, we have something which is quadratic in L2, and we are fine with that. Here we have no phi, but we have just one term, and as it is quadratic in omega, here we are going to find a constant here, replacing by a constant, and then you can conclude that you have a global solution. And where does the constant comes from? And that's the last slide. The constant comes from the Ladyzhenskaya inequality. If we are in H2, but initially, but we may assume that we are initially because we have a local solution in L infinity H1 and L2 H2. So we construct first a little solution on little interval of time, and then we go again with the construction from the new time, but we are in H2. So there is no loss of generality to assume that we have two derivatives in L2 phi. And then Ladyzhenskaya inequality shows that you have this control. The integral of omega square over R2 is controlled just by the initial value. But now, here I have dx. But when r is small, omega over r is like the derivative of omega. So I will find that. But 1 is like phi. So I will kind of what phi. And when r is larger than 1, 1 over r2 is less than phi. So I have that. So this quantity is a constant. So I have a linear ground wall inequality. And then I have a global solution. So you can check everything on the energy balance. That was the idea of the talk. So I just show some references and I can answer the questions.